So hi everyone, sorry for some technical glitches. So today we're going to present the Universal Payload for optimized firmware handoff server platform. So I'm Sheng, this is Arthur. So we both are from 9 Elements. And unfortunately, our another speaker, Vincent, he couldn't make it last minute. So we will present on his behalf. Yeah. So let's get started. So I want to show you about the latest AI innovation in the firmware. No, just kidding. So, so as you know, firmware is a pretty boring technology, as I guess much of you here are firmware engineers. So we survive all those craze, internet crazes like the cryptocurrency and then the AI, which is you heard it everywhere now if you go to the talk everywhere. So firmware will always be as basic as possible because it serves one simple purpose: just boot the system in the 4 different aspects, as you can see here. Velocity, you have to boot as fast as possible. Stability, you have to make sure all your hardware peripherals work perfectly. And scalability, you have to make sure that your firmware is able to scale to everything. And then at top of most, we always talk about security, because many people, they focus on security on the OS level. Like we have to harden the kernel, we have to make sure that we have all the fancy antivirus or security on the OS. But they always forgot that firmware can have a lot of loopholes there. For example, in the x86, we can SMM. That has a lot of loophole. If you can just Google zero-day BIOS, zero-day vulnerability BIOS, so you can see a lot of attack and exploit on the SMM, that you can get the full control on your system through the SMM exploit. So that's a pretty scary. As you can see, over the 20 years, right, the challenges of the firmware. For over the 20 years, there's more and more, not just one EDKII. Actually, Coreboot also was born, but previously Coreboot was called as Linux BIOS. Now it's called Coreboot. And then we have EDKII, which is the Tiano core based on the UEFI implementation. And then we have a U-boot, which is also a lightweight solution that has been widely used in the embedded system. And then who knows, maybe in the next 5 years, there's another boot, whatever boot that just came out more and more. And each boot solution, they have all their own method or on their own format to pass the handoff data to the next stages. For example, U-boot is using FDT, EDKII Tiana core is using hop, and Coreboot is using Coreboot table. And maybe there's another new boot use whatever table, so you never know. And then this adds a more complexity to the next level, which is a payload. So the most prominent payload, as you can see in the market, the first thing is a UEFI payload, and which provides a very comprehensive UEFI interface for the OS, or which is most of you aware because I guess we are here for the server segment, so have a server background. So LinuxBoot is quite prominent in the server market for the firmware. So that means you have to have all these layers that you have to support for all this firmware. And then it becomes a problem. So not only we have to support for ARM, you have to x86 and RISC-V, so all these 3 different architectures we have to support for all this. So why we have to make the firmware more complicated? So today, as 9Elements, we work together with the community, the firmware community, to solve this critical firmware problem that exists before it becomes huge. So our goal is to make firmware simple again. And we are working together with all these prominent open source firmware community, like U-boot, EDKII, Coreboot, and LinuxBoot. All of us come together and we work on this initiative. It's called Universal Payload. So this Universal Payload you can think of like it's like the USB-C of the OSF world. So with just one interface, you can boot in any way. You can from no matter you use U-boot, EDKII, whatever, you can just use Universal Payload, and then you can just boot simply to the payload. So these are the problem statement that we are trying to resolve, to consolidate the complexity on the firmware level, so that we can have a peace of mind and then have a faster porting experience across the different firmware stack. All right, so I will go to stack back a bit. So before we come to this universal payload solution, right? So we had to understand what standard we want to use. The concept is good, we want to unify it, but what should we use as a data handoff structure? Should we use EDKII hop? Should we use coreboot table? Or maybe should we use the latest and most creative one in the market where everyone talk about is called the CBOR? Yes, it's called CBOR. Is there? I can show you later how the history went when we do the pathfinding with the community. It is a very tedious process, trust me, because not everyone is happy with each other's solution. But that is a background I want to give you for now, that this is the problem before we consolidate on one solution. So now I would like to pass to my colleague, Arthur. He will talk to you about the technical part of this.
Yeah, so just to give you an idea of what the kind of problems are and to invent or have a new interface. On the left, you see the existing core boot tables. They have like a tag and a sort of linked list where you just go to the end of an entry and then you're at the next one. Has a problem that it's GPL licensed, so it cannot just simply be included in all kinds of solutions because the GPL, of course, requires all software to also be GPL licensed, which isn't always the case. And that's on the core boot table side. It's even called LB tag because it predates even core boot. It's called when it was still called LinuxBoot. On the other hand, we have the UEFI handoff blocks. They are specified in the EDKII source code, but they have a 64K size limit. Now that's not really a problem for handing off data in this case, but it's still a limitation of this data structure. And it uses a 16-byte GUID to tag certain entries. One problem is you sort of need to know in beforehand what you'll be expecting. So both the code producing this data as the code consuming this data needs to be aware of it, and you need to write code for that. So what's the expectation of this universal payload design is to have something self-describing, which essentially means that you could just, even as a human, sort of parse it and see what it's all about without having these predetermined structs determined in C structs, for instance, to pass data. And it should also be something that's specified somewhere else, because we don't want to really maintain a new way of passing data. We should use something that already exists and is available in as many programming languages as you want. So having lots of libraries available is a requirement goal. So what would be the examples of data we pass on from, let's say, the hardware-related part to the payload? Well, that would be, for instance, the memory map, some build time information, like what tooling did we use, when did we build it, what version of the code did we use. Often payloads want to print stuff to a console for debugging purposes. And, you want to use the same console as your firmware initialization, so that information needs to pass on. And, that's not really applicable for most OCP hardware, but on laptops you will probably want to pass on some frame buffer information so that the payload can just show things on your display. And the goal is also to be able to easily implement this in all kinds of payloads, and a few are listed there. So, mandatory slides. Are we going to invent a new standard and then end up just with one more standard that confuses everyone? Please no. So that's we try to avoid. So we don't want to reinvent the wheel, and that's why we looked at existing solutions. And while looking at these existing solutions, we noticed that the scope might actually be broadened to use it for other parts of the hardware in it. Because what is our solution? It will be the flattened device tree, which is a standard that started in 2005 in the open firmware and is hosted on devicetree.org. well, libraries already exist and are already integrated in most of the hardware init projects, like EDKII, coreboot, and uboot all have device tree integrated. Device tree is used to describe the hardware configuration, but also yeah, some other parts like how it, what has been enabled, what not, what what space in memory is consumed, and this kind of things. It's available in a lot of programming languages, so pretty much all language you reasonably use in firmware have already a library for it. It's one of very nice advantage of device tree is that it is human readable. So you have a device tree source, which is just a plain text file that anyone can read, and it gets compiled into a binary by the device tree compiler, which is called DTC, and the binary is called DTB. And well, it's not just something that's used by the open firmware standard, it's used pretty much everywhere. A lot of real-time operating systems like Zephyr use it. It's ubiquitous in Linux. So we're really trying to reuse everything that's already there. One thing on top of that is that the bindings, which are used in device tree to describe hardware, so I'll go over that, what that means later, are already defined. So we can just reuse a lot of other specifications to, for our use case. So one example would be this. This is an example of a certain node in device tree. So you see that it's a memory node. So that's the memory at 0. So which will be a unique name for a node. And below that node, you can have other nodes, so child nodes, but also properties, which can be both text, booleans, and integers. And the size of the integers are configurable so that it supports both 32 and 64 bits. And this is an example of a node that describes where our DRAM is located in memory, which a payload needs. So we have currently written a proof of concept, and it has the current flow. So as we said, device tree is something you can really write by hand. So in this example, we created the device tree structure, compiled it into the binary. During runtime, we unpack it and make it into a linked list so that we can easily add nodes or add properties. After we have done that, so described our current hardware and its current configuration, we pack it up again into a new DTB, and that can be passed to the payload. So it's really flexible, so it can be done at build time or at runtime. And yeah, we've defined a few useful nodes and useful properties inside one of the links there, or based on Zhang's work. Yeah. Okay, I'll pass this on to. Oh. Okay, yeah, I can talk about this.
So this is just an example for you to look at. So I guess most of you are already familiar with this, about the EDKII payload flow. So basically the payload interface that you can see, what we actually use is actually at the payload interface. You can see after the bootloader, between the bootloader and the payload. So that is actually where the universal payload tries to solve, which is the interface between these two. And this is just a future example. So this is also part of the Vincent's slide. So in the future, that maybe this can be replaced the Intel FSP because of the highly configurability for the FTT as well.
I can talk about it. Huh?
Oh yeah.
Yeah. So what are UPDs? This is basically platform-specific struct that is used in the configuration for running FSP, which does the hardware init part on Intel platforms. Now each platform has its own structs of UPDs, which means that code reuse is really hard because well, when structs are different, your code just will not compile if you're dereferencing struct entries. This would be improved upon a lot if the configuration of FSP used device tree structure, because device tree, you can think of it as a flexible node, a flexible struct where adding entries is very easy. And that would make the interface to configuring FSP just very reusable, both on the code front, but also on the way people configure things. So one useful example would be if Intel wants to verify all the FSP options, it needs to, well, build binaries for every option because they're filled in at runtime. This would just allow them to work with a text file, and automating text file and then running it on real hardware would, for instance, improve their ability to test all the options a lot. So, yeah, that's just an example of how an FSP configured by device tree would look like. I think it's taken from the U-Boot project, which pioneered this idea, where basically all the UPDs are translated to a device tree node property. And yeah, so okay, yeah, you can do this one.
Yeah, so so Universal Payload will be part of the Intel Universal Scalable Firmware solution that roll out to their customer. So this is the one you can see that Universal Payload firmware fits in one of the expect as circle as read in the Universal Scalable Firmware framework. So for sure, Universal Payload is not just work on Intel x86. It can be easily extended to fit into the ARM, for example, ARM system ready baseboot requirement solution. That because it's just the interface between firmware to firmware, so you can easily incorporate into that for sure. All right, so you can see on the left, the top right is the official Universal Payload logo that we just designed together, and this is actually the first time forever in 20 years that all the firmware community, which never talked to each other before, that came together and work together, and come up with this Universal Payload spec. And then this will be architecture agnostic. It will support with ARM, x86, and RISC-V. And then in our meeting, we have engineers from Intel, ARM, Revos, us, Google, Siemens, and Samsung. So these few engineers come together. And then, so as you can see right from here, the timeline. We actually started in March not 2023, but 2022, which is last year. And then last year in September 2022, we actually already present in the OSFC, Open Source Firmware Conference, for the broader feedback. But what do you see that between the September 2022 to August 2023, that is exactly the 1 year gap. Why did that happen? That was not expected. Because if you think of this reality, right, each of every firmware community, they have been working with their existing solution for many, many years. And then if you just come in and then say that, okay, why not you just accept FTT? It doesn't make sense. You have to discuss with the communities months and months and weeks, go through hundreds of mailing lists to justify why this is better for everyone, how can this solve the velocity and development for the firmware. So these are a lot of hurdles that was never part of the expectation that we have to go through. That's why it has to go through until 1 year delay, and then it's like one meeting per week that we have to do that for 1 year. So it's pretty exhausting, but in the end, the result is quite fruitful in a way. So for now, we are targeting. We actually already released the version 0.8 spec to the public. I can share to you the link later. And then by March 2024, our target is we will finalize the handoff spec 1.0. So currently, the code, because we believe in the principle that code first, right? Because we can just talk forever with the spec, but the code has to go in at one point. So at this point, the U-Boot already has a code ready to check in, and EDKII as well. They will upstream some patches soon, and Coreboot as well. The patch is ready for review. And we have been working tirelessly with all the companies together and the different silicon companies to get this thing, to make sure that everyone's interest is aligned together on this. So in conclusion, this fits perfectly in the spirit for OCP. So it's an open development, And it's a cross-community collaboration. And with a good willing people, and then the gesture of trust that we're built on, and then it's by the community for the community. And what we try to do is very simple, to make firmware as simple as possible for everyone to use. Because firmware shouldn't be complicated. It should be just easy to use, easy to port, and easy to develop. So that's it. That's what we have for now. And then if you can look at this, this is the spec that we have for public. So everything is public now. Go in here, take a look at the spec, and feel free to submit any pull requests you have. That's it. So, yeah, thank you. Any question?
Thank you. I think we don't have time for the questions. I think we need to
Okay.
Okay. Thanks, everyone.